Welcome online lectures wireless mobile communication. Uh, in previous lecture, we have seen the three equations, but here we are going to drive the equations for the FRII'S transmission formula. So start from beginning. It is a proof for FRII'S equations. You can say it is the derivation. It is the derivation of your FRII'S transmission formula. So here I will write the FRII'S transmission formula. ये FRII'S transmission formula, it is for the free space propagation. एग्जाम में आपको पूछा जाता है, ये इसका डेरिवेशन है. डेरिवेशन और भी तरीके से है, हम सारे डेरिवेशन एक के बाद एक देखेंगे. So there should be two ends. First is the transmission and second one is the receiver. And both having the antenna which transmit, and transmitter antenna is transmitting it is the isotropic source. So it radiates in all the directions. Receiver receive this transmission signal. So it also having a antenna. This end is known as receiving and receiving antenna. Receiving antenna and this end is where actual transmission is taking place. ये आपका कहलाएगा transmitting antenna. जो लोग इस लेक्चर को देख रहे हैं, अगर उनको इसके इंट्रोडक्टरी पार्ट को देखना है तो वो लेक्चर नंबर 7 जरूर देख लें. एंटीना, transmitting antenna. So this is the electromagnetic waves radiations which radiate in a free open space and it will be felt on your antenna. The separation distance between the transmitter or receiver is called D. Okay, so it is transmitting source is isotropic source so here we have the transmitter receiver system. So this figure is a figure number 1, that is the transmitter and receiver system. So started now. The power density is measure of amount of power per unit volume. So the power density is first to calculate in per unit volume. So power density is the measure measure of amount of amount of per unit volume. Per unit volume. Consider if we consider transmitting antenna if we consider the transmitting antenna as a isotropic source as a isotropic source, then power density at receiving end will be given by the formula of the receiving antenna is W is equal to transmit power P of T to the area A. So it is nothing but power density of transmitted system, and that is isotropic in nature. So power received is to surface area, and surface area is 4 pi 4 pi d square. Four pi d square. So it is valid only for isotropic, valid for the isotropic antenna. isotropic antenna. That is nothing but power received to the surface area. You can say the power density can be defined in the ratio power received to the surface area. Surface area. So this equation is derived for the direct line of sight. So you can say if gain of transmitted antenna is g of t, then then power density power density is omega is pt effective aperture of antenna to the surface area under ideal condition. We consider under the ideal conditions, then the effective aperture of antenna of receiver antenna is A of C. If effective aperture of antenna is AC, then received received power can be written as E of R is the product of power density and effective aperture of receiving antenna. So to distinguish this aperture, here we can put the transmitting aperture of effective aperture of the transmitting antenna. So now the term is which is in the terms of E of t, G of t, 4 pi t square into a CR. Why? Because we put the values of this term value of these terms in the equations. So we write this effective aperture. So you can say gain of transmitting antenna is G of t is equal to 4 pi aperture of effective antenna of the transmitter divided by the lambda square. So putting this G of gain of into this equations, you can see 4 pi A of effective aperture of transmitter divided by 4 pi d square lambda square and product of effective aperture of receiver. So if we take the power down, power of receiver to the power of transmitter, then the ratio is this 4 pi is cancel out. So we have to write here A C A E effective aperture of transmitter, effective aperture of receiver, separation distance of transmitter receiver का square and wavelength का square. So we are getting this formula. Now see the gain of your antenna. Gain of receiver antenna, that is the G of R, is 4 pi A of E, and it is the R divided by lambda square. So putting this terms, power of receiver to the power of transmitter in the equation in terms of effective antenna, then it is coming gain of transmitter and product, but it will become the product of transmitter and receiver, and 4 pi d upon lambda square. So this is equation A, and equation A is the transmission formula. Now move towards the transmission path loss. Transmission This transmission path loss can be derived if you know the FRII'S transmission formula. Path loss we know that the FRII'S formula is formula it is given by received power to the transmit power is equal to gain of transmitter, gain of receiver to the 4 pi separation distance to the lambda का whole square. This is calculate in decimal because it is in random, so it's not calculated. So take the decimal and base 10. So it comes to 10 log. We take the log of these equations. 10 log E R to the P of E is the 10 log of GT by GR to 4 pi D square of whole D square lambda. So you can write 10 log PR to the power of transmitter is equal to 10 log of transmitter plus 10 log of gain of receiver minus 10 log of 4 pi d upon lambda का whole square. So you can write once again 10 of L log of received power to the transmit power is equal to 10 log of received power plus 10 log of transmit power plus 20 log of this 4 pi d. Now our formula is rearranged. We take the inverse of this 1 upon, so it is changed, and this term is explains the transmission loss. This term explain the transmission loss. So again we write 10 log of received power to the transmit power is equal to 10 log of transmit power plus 10 log of gain of, sorry, 10 log of gain of transmitter and 10 log of gain of receiver, and it is shown by the minus path loss LS. So here means means LS is statistical transmission attenuation loss. Transmission, transmission, attenuation, attenuation loss. So derivation of minus LOS how to derive this transmission attenuation loss. To start, first of all, minus transmission attenuation loss is nothing but it is the 20 log of lambda to 4 pi d. Okay, so here f is c by lambda, or you can say lambda is c by f, that is 3 into 10 की power light of the speed meter per second. So we rewrite putting all the terms and equations in the form of frequency. So it is the 20 log of 3 into 10 की power 8 divided by 4 pi into 1 upon kilos per frequency. Now consider if frequency f if frequency is considered in the megahertz and distance in kilometer distance in kilometer, then you write the equations like this way: minus transmission attenuation loss is written 20 log of 3 into 10 to the power 8 divided by 4 pi, again multiplied by 1 upon 1 kilometer d to the power 3, frequency f in megahertz, 1 upon 6, and turnover frequency. So अगर if we compute this, we write transmission attenuation path loss 20 log into 3 into 10 to the power 8 divided by 4 pi multiplied by 10 to the power 9 and 1 upon turnover frequency. So we can say after the simplification, transmission attenuation loss is written as 20 log 3 divided by 40, 3 divided by 40 3 divided by 40 pi. क्यों? क्योंकि यहाँ पे 8 है, यहाँ 9 है, ये आपस में अगर कटेंगे तो एक बचेगा 10 to the power 1 is 10 and multiplied by 20 log of distance in kilometer minus 20 log of f megahertz. Okay. So after again simplifications, this is nothing but minus 32.44 minus 20 log of distance in kilometer minus 20 log of frequency in mega hertz. So हर एक टर्म में माइनस दिख रहा है, माइनस इधर से लेंगे, माइनस इधर से लेंगे तो माइनस माइनस आपस में कैंसिल आउट हो जाएगा. So minus sums are cancel out to each other in the both the side, left hand side and the right hand side. So this equation is can be written as 32.44 plus 20 log of distance in kilometer plus plus 20 log of f in megahertz. A unit of this plus 20 log of f in megahertz. This is calculated in dB. This is the transmission path loss. This is the transmission path loss. So the transmission path loss is derived, and you can see the transmission path loss over a flat open area or water. It seems that this path loss varies 20 dB per decade with this distance, and same as that of the free space path loss. So it is implied that the propagation path loss for the land to the mobile propagation over a water varies as a 20 dB per decade or 6 dB per octave with the distance between the transmitter and receiver. So this is actually happened same as that of the free space path loss. So it is the conclude here that the path loss for land to mobile propagation over a land in normal terrain is 40 dB decay as per the 2 days propagations model. So it is different from land to mobile propagation over the flat over, or you can say water, is 20 dB per decade. So now see the one numerical on path loss. and received power and transmission delay. Transmission delay. Problem is a wireless communication base station transmit transmit 10 watt of power at a carrier frequency is 1 gigahertz frequency of 1 gigahertz if the receiver station receiver station is at a distance of 1.6 kilometer 1.66 kilometer from the base station then determine first the propagation path loss, the propagation path loss and the MA 3 space environment. So first of all, we have seen the power path loss. Second is the received signal power. It is also in dVm. The received signal power in dVm. And third is the transmission delay in nanosecond. Third is the transmission delay in nanosecond. Solution. So transmitter output power, that is the P of T, is given that 10 watt और इसको हम लिख सकते हैं 10,000 milliwatt में. Transmitted gain antenna, transmitter that is G of T is UN 1.6 receiver antenna G of R is unity, so it is same 1.6 carrier frequency is 1 gigahertz. Let's see 1 gigahertz should be calculated in megahertz. To convert 1000 megahertz and separation distance between transmitter and receiver is given that is small d. So small d is 1.6 kilometer. So calculate the propagation path loss in dV in a free space environment. So first of all, to convert power watt in dVm, P of t is converted in P of t in dVm. So कैसे करते हैं इसको? Power of transmitter in dVm is given by tan log of P of 1 milliwatt. So P of t dVm is written tan log A O E star, that is 10 to the power 4, so it becomes 40 log of 10, so it is plus 40 dVm. So P of t is in dVm. Now convert gain so to convert G of t ratio in G of t dV decibel. So G of t dV is 10 of log G of t ratio, okay? That is tan log of G of ratio is 1.6, that is 2 dB. Or to to convert G of R ratio in G of R dB. So G of R dB is equal to 10 log of G of R ratio, that is 10 log of 1.6. It is equal to 2 dB. So G of R is 2 dB. Now path loss in dB, that is 32.44 plus 20 log of d kilometer plus 20 log of Fraunhofer equations in megahertz. So 32.44 plus 20 log 1.6 kilometer plus 20 log of 1000 megahertz. So after the simplification, 22.44 plus 4.08 plus 60 is equal to 96.5 dB. It is the path loss in dB. Now, B part, B part power of receiver is in dBm. So power of receiver transmitter in DVM plus gain of transmitter dV plus gain of receiver dV minus path loss in dV. So it is 40 plus 2 plus 2 minus 96.0 96.5. So it is around minus 52.5 dBm. So calculated in dB. C part in 1 nanosecond transmission delay. So transmission delay T is equal to 3.33 nanosecond per meter of distance for 1 kilometer means 1000 meters distance this is multiplied 3.33 into 1000 meter. It's come 5.33 nano. Sorry, not in nano. 24 minus 6. Coming micro second. So it is the end of the lectures. Thank you very much.